How you doing, everyone? This is another one again, the journals and articles we've read in the Paleo Club here at San Diego Museum of Natural History. So, and basically we just kind of get together and talk about some published stuff that's been out in scientific journals. We discuss about them. This is people like me, like volunteers, also some of the staff who are paleontologists themselves or work in, or graduate students. In fact, this is run by a couple graduates. Now, this first one here is there's geophysical research letters. Let's see, the authors Julia Brugger, George Fuellner, and Stephen Petrie. Let's see, this one is, and this is kind of one of those where it's one of those titles you shouldn't want to put in a scientific journal. Baby, it's cold outside. Climate model simulations of the effects of the asteroid impact at the end Cretaceous. Yeah. Usually not a good idea to put that in regular newspaper articles, so let alone scientific journals. Let's see. This is about the Chicxulub meteor, which is the famous meteor that we all know that hit the Yucatan Peninsula, Chicxulub, and pretty much killed. It helped reign the end of non-avian dinosaurs and many other things at the time. This is a climate model simulation where they use sulfate aerosols using coupled climate. Let's see, explore long-lasting cooling due to sulfate aerosols using a coupled climate model. And let's see. And they figured that the global annual mean surface air temperature decreased by at least 26 degrees Celsius with 3 to 16 years sub-freezing temperature and a recovery time larger than 30 years. And this also, there's a mixing in the oceans that resulted from this that would also allow huge plankton blooms because of the upwelling of nutrients. Let's see. So basically, it's the same with this type of the new modeling that they're doing. They use it to see the measuring how cold it got after the Earth was impacted by this meteor and how long it took to recover. And the looks of it shows like, okay, it cooled off quite drastically, except that it kind of cooled off too much. I think one of the graduates discussing there that the temperatures they say that it cooled down by would have turned this planet into a snowball. There's another flaw in this that was discussed that in the paper. Let's see if I can find that. Two recent studies use TEX86 paleothermometry of shallow marine sediments to estimate sea surface temperature change across the Cretaceous Paleogene boundaries from the Brazos River section in Texas. Valley Coop et al. Reconstructs pre-impact temperatures at 30 to 31 degrees Celsius in good agreement with the late Cretaceous sea surface temperature from well-preserved foraminiferia. So yeah, there's a few degrees off. 26 degrees Celsius was climate, mind you, not just regular temperature. And other studies that came out just from a couple of years ago, 2014 to 2016. So, and it shows that it was around the surface temperatures at that time was 30 to 31 degrees. Major difference as far as worldwide climate. So there's some study right here that I'm reading of is a drastic difference and should be raised questions about. You know, that the model may not be, even though it shows global cooling results, it may went overboard and may have taken other effects in mind. They also discuss here that, you know, that, bear in mind, they're just studying what they're modeling just by the meteor impact alone. There's another factor that helped bringing minds to dinosaurs and many animals that made extinct at that time, and that is the Deccan traps in India, where there was active volcanism. And you have that acted in concert with the meteor impact when it hit. So I think the model is just too simple and too narrow focus to really try getting accurate information. I'll post it down below, as normal. The next one is a bit more interesting. Live birth in archosauromorph reptiles. First, and this is by published by Nature Communications in 2016, and received September 2016, accepted December 2016, and it was published in February 2017. This just came out. You might have found this in the news. Live birth has evolved many times independently in vertebrates such as mammals and diverse groups of lizards and snakes. However, live birth is unknown in the major clade of Archosauromorpha, a group that first evolved some 260 million years ago and is represented today by birds and crocodilians. Here we report the discovery of the pregnant long-necked marine reptile Dinocephalosaurus from the Middle Triassic, now 245 million years ago, of southwest China, showing live birth in archosauromorphs. Our discovery pushes back evidence for reproductive biology in the clade by roughly 50 million years, and shows that there is no fundamental reason that archosauromorphs could not achieve live birth. Our phylogenetic models indicate that Dinocephalosaurus determined the sex of their offspring by sex chromosomes rather than by environmental temperatures like crocodilians. Our results provide crucial evidence for genotypic sex determination facilitating land-water transitions in amniotes. So yeah, we give humans, being mammals, have live birth, but the question is, how far back does live birth go? And here they found a Dinocephalus. This is not the first of its species, but they just found one. And I have to admit, with the people in the group, the pictures aren't perfect. Sure, in the PDF that you can get, you can zoom in on it, but unless if you had a physical paper, it'd be much harder to find. This specimen was found in situ, I believe, but it's not complete. At one point, that layer of strata that contained it was exposed, and parts of it were withered away, and then sediment came back and filled in those gaps. So they only have bits and pieces, but what they do have is pretty fascinating. Inside its gut is a smaller version of Dinocephalus. Now, it is positioned at the right spot of its belly. It's not head first, because if you're in the water and you are like a fish eater or something like that, usually things go inside head first. So, and this wasn't. This would have been given. Its live birth would have been breached, when it was live. The animal will probably remind you of an Elasmosaurus. In the fact that it has a very long neck, but it doesn't have the well-formed flippers that Elasmosaurus and other of a kind have. Just to give you a description of this. But it's pretty fascinating. I think the best part about, is, here we have evidence that it, gave live birth. And it would make sense that it would be live birth because this is an ocean-dwelling animal. We figured this because of, I guess the sediments gave a marine environment. Not to mention, if you look at this animal's long neck, it would not be, it's very long, very narrow, would not have been sufficient enough to go on land and lay its eggs. And then you also have to make sure that it's protected in some fashion. So this is probably one of the earliest amniotes that had a live birth. Not the first one, you never can't assume that. But it's fascinating to see, okay, live birth goes back to 245 million years ago. That's great. And because of the fact that, unlike crocodiles, who they rely on the temperature variations where their offspring is male or female, this one would have to be based on just the chromosomes as given. So there's evidence for that, because the waters would not be would not be a good way to rely on temperature variations. Now, I haven't read the, I've only read the, let's see, the discussion once. And they said that it's kind of tacked on, just to finally put one in because the journal requires it. But read it down below. Just the fact that something like this is around is pretty fascinating. Now, the third one I'm going to admit I didn't read because I didn't read my emails in time before the meeting. And this one is not a journal article. This is from sciencemag.org, I think. Yeah, sciencemag.org. And it's a nice little 3-page article about the Mesozoic aviary. Biomechanical models are key to understanding how dinosaurs experimented with different ways of flying. And this is great for lay people, because a lot of people may not understand the fact that just because something had feathers that it immediately gained for flight. No, feathers started out for insulation, and then it wasn't until later on that certain groups, that certain species later had the types that allows them some form of flying. And they give a nice little phylogenetic tree here. You got in dinosaurs, it shows Cretaceous, which is a ceratopsian from Asia. Had probably these long, long little strands that maybe an expanded primitive feather, but it didn't branch out or anything, and so it's there on its tail only. Could not fly. Dilong, which is a T-Rex early ancestor, whatever feathers it had, couldn't fly. Ornithomimus and Caudipteryx, they can't fly. They were too big, and so your feathers, you had insulation, could way to help nesting of their eggs. But it wasn't until you got paravians that have the means to develop, the means that expands to flying or to powered flight later on. Now, if someone like me, I already know this for a long time, but I have a lay person, this could be a good, simple article to read if it's not too complicated. Well, there you have it. That's the Paleo news for this week, and I'll list them all down below. And again, I'm doing this because for us paleophiles, we can always read in news articles, but they don't always translate it right. I say take the time and learn the best you can by reading to the main source itself. Thank you very much for watching. Y'all have a nice day.